On November 18th, NASA announced the first signal detected on ThreeI Atlast and its impossible structure. ThreeI Atlast is almost flat, with the ecliptic plane carries a dense core rich in nickel and iron, and with very little water continuously showing a non-gravitational acceleration that is hard to explain. Telescopes from Earth to Tianwen-1 and HiRISE observe Atlast emitting straight stable jets, even pointing close toward the Sun, behaving like a controlled propulsion system, rather than chaotic outgassing. After surviving perihelion, Atlast suddenly whispered with a delayed phase hydroxyl signal, then accelerated with a stable anti-gravity behaviour, before returning to a purely gravitational orbit and shifting to a metallic blue glow, as if revealing an ancient alloy core. Isotopic analysis shows that ThreeI Atlast may originate from an old stellar system about 7 billion years old, and the backtraced orbit passes close to the region of the sky, where the 1977 WOW signal appeared, making the disguised Bracewell probe hypothesis a possibility that cannot be ignored even when mainstream science still tries to keep it within the frame of natural but extreme. Right now, we will continue the journey of exploring the mysteries of ThreeI Atlast before NASA's latest announcement. At first, ThreeI Atlast looked like one more faint visitor slipping through the outer dark, a speck that would be logged named and soon forgotten. Then the numbers began to disagree with the story on the screen, and Atlast slowly pulled the entire astronomy community into its gravity. Under normal circumstances, a comet enters the solar system on a long, graceful path leaning out of the ecliptic like a tilted thread of ice. Atlast did something different. Atlast followed a retrograde orbit flowing against the general rotation, yet its path sat almost perfectly inside the thin plane where the planets travel. The angle was small, just a handful of degrees, but the precision made many orbital dynamicists stop and stare. In crowded conference calls and late-night emails, people compared Atlast to every catalogued comet they could think of. Tables lined with perihelion distances and inclinations marched by, and Atlast remained an outlier that refused to blend in. ThreeI Atlast crossed the planetary lanes at just the sort of angles that made some researchers whisper about alignments, while others insisted they were seeing nothing more than chance. The early images were not beautiful, but they were enough. A faint condensed head and a suggestion of a developing tail told the basic story of a sun-warmed nucleus beginning to wake. Yet as more observations were added, Atlast started to contradict the simple picture. The brightness did not rise and fall the way a loose dusty comet core would normally respond to sunlight over time. Spectra brought new pieces of the puzzle into view. The ratios of elements and molecules that seeped out with the gas did not fit the chemical profile that comet modelers like to use as a template. ThreeI Atlast seemed unusually rich in heavier metals and unusually poor in easy familiar ice, as if it had been forged in a very different nursery from the comets that circle near our own sun. On paper, the values could still be squeezed into the edges of natural variation, but the fit grew more uncomfortable with each new data point. While the data accumulated, voices also emerged to guide the narrative around Atlast. Avi Loeb, already known for inviting bold interpretations of interstellar visitors, pointed at the pattern of anomalies and suggested that the safest approach was not to rule out an artificial origin too quickly. In contrast, other astronomers, including Jason Wright and his colleagues, urged everyone to stay anchored in known physics and to search harder for ordinary explanations before entertaining extraordinary ones. ThreeI Atlast became less a cold object in space, and more a mirror held up to the scientific method itself. Night after night, telescopes turned and followed Atlast as it crept inward. Each new track on the sky added another line to a growing ledger of small disagreements with expectation. Together, those tiny discrepancies began to feel less like random noise and more like a quiet pattern asking to be heard. Without raising its voice, Atlast was already rewriting the questions astronomers would carry into the next observing run. In the weeks after discovery, astronomers began to realize that the numbers behind ThreeI Atlast were stranger than the first images suggested. Atlast was no longer just a pale streak on the screen, but a set of physical and chemical measurements that refused to sit comfortably inside any familiar box. When telescopes separated the light of ThreeI Atlast into its spectrum, the fingerprints of different elements and molecules appeared in thin, quiet lines. Those lines told a story that felt slightly wrong to anyone used to reading ordinary comets. Atlast seemed to carry an unusually strong signature from heavier metals, especially nickel compared to the amount of lighter material that should have dominated a cold, fragile body from deep space. In typical cometary chemistry, water is the faithful companion. Ices melt, vapor rises, and water makes up a generous share of the gas that pours away from the nucleus. ThreeI Atlast, however, appeared to release only a modest fraction of water, on the order of a few percent, dwarfed by more complex and less volatile components. The numbers could be made to fit a natural origin, but the fit felt stretched like a model pushed just beyond where it was designed to go. As the data improved, dynamicists weighed the mass and density that would be required to match the observed motion of ThreeI Atlast. The object began to look far more massive than the other interstellar visitors that had passed through the solar system in recent years. Atlas needed to be dense enough to hold together under its own spin, and the pull of the sun, yet compact enough to show only a relatively small active surface. This combination led some researchers to picture a hardened core less like a loose snowball, and more like a welded remnant of something that had survived a long and violent history. Tracking software drew the path of ThreeI Atlast across the solar system, updating as new astrometric points arrived. Instead of following a purely gravitational curve, Atlast began to drift in a way that hinted at a persistent gentle push. The deviation from the predicted orbit was not wild, but it was steady, and that steadiness troubled people who spent their lives trusting gravity to be clean and simple. Several teams checked whether ordinary outgassing could explain the extra acceleration, and for a while those models sat on the table like a comforting explanation. Then the comparison with other comets raised a deeper question. To produce the observed non-gravitational acceleration ThreeI Atlast would need to shed mass in a controlled and sustained pattern. For sun-grazing comets that skim almost directly through the furnace of the solar corona, such intense activity can sometimes be justified by the enormous heat input. Atlast, on the other hand, received far less energy from the sun, yet the orbital drift threatened to rival, and in some estimates exceed what those more reckless comets display. This mismatch made ordinary explanations for ThreeI Atlast feel thinner with each iteration. A few researchers suggested that perhaps the measured acceleration was being overestimated, while others wondered if some part of the outgassing geometry had been misunderstood. Atlast, patient and distant, offered no clarification, only the same steady curve bending a little away from the line that gravity alone would have chosen. In response, some analysts proposed that ThreeI Atlast might possess a surface broken into confined vents and deep channels, allowing stored energy to escape in narrow directed streams rather than in a loose chaotic plume. Such a configuration could in principle push Atlast in a particular direction without demanding a catastrophic loss of material. Yet the precision implied by those models made even their authors uneasy, because the behaviour of Atlast began to resemble the output of a controlled system, rather than the random sputtering of an icy relic. The debate circled late into the night in observatories and offices around the world. Some voices insisted that the chemistry and dynamics of ThreeI Atlast must still sit within the vast unexplored space of what nature can do. Other voices pointed out that each new measurement seemed to widen the gap between Atlast and every benchmark comet in the catalogues. Somewhere between those positions, the community tried to rest on a moving line, watching Atlast glide inward and waiting for the next clue to decide whether this object was simply unusual or quietly impossible. The first close analyses of the coma around ThreeI Atlast brought a new kind of discomfort to the data tables. Observers had expected a soft, diffused mist fanning away in the direction opposite the sun, the usual signature of a warming comet. Instead, ThreeI Atlast showed narrow, bright structures that looked more like columns than clouds, as if something rigid had been drawn across the sky. As more images poured in, astronomers began to stack them over time. The rotation period of ThreeI Atlast, measured at roughly 16 hours, meant that different parts of the surface should turn in and out of sunlight through each spin. For an ordinary nucleus, that motion tends to twist and blur any jets into curved, spiraling shapes, tangled by rotation and by the relentless pressure of the solar wind. On the screens, ThreeI Atlast did not cooperate with that expectation. The bright features appeared as straight, unwavering streaks stretching over distances measured in millions of kilometers. The shapes kept their orientation with a calm that seemed almost indifferent to the spinning core beneath them. Where a familiar comet would express its rotation in corkscrews and arcs, Atlast presented almost ruler-straight beams. Teams tried aligning frames at different times to see if a subtle twist might be hiding in the noise. ThreeI Atlast continued to show the same narrow columns as if the gas were anchored to some invisible rail, rather than to patches of ice on a turning surface. When lines were drawn to project the direction of the brightest streak, those lines pointed disturbingly close to the sun itself. The idea of a jet pointing toward the sun defies the simple picture that many people carry of a comet tail. In textbooks, material always streams away from the solar furnace pushed outward, like smoke caught in a steady wind. 3I Atlast appeared to be doing something closer to the opposite, holding a line that leaned inward instead of away. To rescue familiar models, some researchers proposed that 3I Atlast might have deep fissures channels that guided the gas so precisely that the outflow compensated for rotation. In this view, Atlast would act like a spinning sprinkler whose nozzles were aligned just right, so that the pattern on the ground still formed straight tracks. Computer simulations attempted to shape such flows, but the degree of tuning required made the scenario feel delicately balanced, almost unnaturally so. Others suggested that debris from an earlier outburst might be following a very narrow orbital path, leaving a dormant streak that only looked like a fresh jet in shallow images. If that were true, 3I Atlast would simply be passing through its own trail, lighting up a pre-existing structure with reflected sunlight. Deeper analysis, however, showed signals consistent with ongoing gas release, not just inert dust reflecting light from a previous event. The solar wind itself added another layer of tension to the interpretation. Measurements of the local environment implied that any loose plume of gas from 3I Atlast should be twisted, pushed, and gradually peeled away along the flow of charged particles from the sun. Instead, the brightest features associated with Atlast appeared to resist that soft violence, holding a confidence in their alignment that made plasma physicists frown. Some teams went back to older cases of so-called backtail comets, searching for analogues that could normalize the behavior of 3I Atlast. There were objects with tails that wrapped around objects with complex geometries, objects that briefly showed apparent sunward features in particular viewing angles. Yet the combination of length, sharpness, and stability seen around Atlast refused to sit neatly next to any of those examples. In quiet conversations, a phrase began to circulate. The jets around 3I Atlast looked less like an accident of melting ice and more like the output of a disciplined system. A disciplined system in engineering language is one that holds a desired state against disturbance, adjusting continuously to keep a target. For a natural comet, the target is usually chaos, a kind of noisy balance of random vents opening and closing as sunlight wanders across the surface. For 3I Atlast, the persistence of those straight sunward features hinted at something closer to control. The idea did not require intelligence, only an internal structure capable of channeling energy and material in a remarkably consistent way. The more the images were processed, the more that consistency stood out. Stacks of exposures spread over many rotations of 3I, Atlast continued to align the same bright lanes in nearly the same directions. Even when the signal dipped and the background grew noisy, faint extensions of the same pattern could often be teased out of the data. That did not prove anything beyond doubt. Nature can, on rare occasions, produce outcomes that resemble careful design simply because the rules allow odd corners where chance can gather. Still, the behavior of 3I Atlast demanded that astronomers decide whether they were still looking at a comet or at a phenomenon that needed a new category. The question did not have to be answered immediately. Telescopes would continue to watch, and models would continue to evolve. But as the first chapter of observations closed, the stable sunward jets of Atlast stood like quiet pillars in the discussion, marking a boundary where familiar comet physics faded, and something more unsettling began. Long before 3I Atlast crossed the boundary of the solar system, theorists had played with an idea that sounded like quiet science fiction. In the late 20th century, Ronald Bracewell proposed that an advanced civilization might send out autonomous machines to wait in the dark between stars, listening and watching for signs of younger cultures. Those theoretical machines were called Bracewell probes, and for decades they lived mostly on the pages of technical papers and speculative essays. When astronomers began to list the growing anomalies around 3I Atlast, the old idea quietly drifted back into the room. A retrograde orbit almost perfectly aligned with the planetary plane, a dense core that behaved more like a hardened remnant than a fragile snowball, and jets that held their direction as if anchored to some internal frame, all suggested that 3I Atlast did not fit comfortably inside the comet template. For some researchers, the pattern remained a challenge for natural models, while for others the pattern sounded like the checklist for a patient instrument. In principle, a Bracewell-type probe would need to do exactly what 3I Atlast appeared to be doing. Such a machine would travel for ages through interstellar space, crossing radiation storms and gravitational tides, and still arrive in working order. To accomplish that, the designer of a probe would give the craft a compact, durable structure a controlled way to manage energy and thrusters, subtle enough to fine-tune a trajectory without advertising every maneuver. When observers watched the steady non-gravitational acceleration of ThreeI Atlast and the unnaturally straight jets, some of those requirements seemed to echo in the data. Of course, there is a wide gulf between a suggestive echo and a conclusion. Avi Loeb argued that the honest path was to keep the artificial hypothesis on the table as long as natural explanations continued to fail. Jason Wright and others responded that extraordinary claims about ThreeI Atlast demanded more than a handful of puzzles and a resemblance to a thought experiment. The debate did not revolve around whether a Bracewell probe could exist, but around whether ThreeI Atlast had earned the right to be suspected of being one. Still, once the question was asked, the scenario became hard to ignore. A Bracewell probe would not need to shine or broadcast constantly. A patient device would spend most of its life in silence, waking only when conditions aligned in a particular system, perhaps when a young civilization began to emit radar and radio into space. The timing of ThreeI Atlast arriving in an era when humanity has ringed its own planet with instruments and begun to send spacecraft outward added another thin layer of unease. Some scientists imagined ThreeI Atlast as a messenger that never expected to be recognized as such. In that picture, the outer shell of Atlast might be designed to imitate the behavior of a natural comet, closely enough to pass casual inspection. Only under sustained high-resolution scrutiny would the control systems, the disciplined jets, and the persistent orbital drift begin to reveal a deeper intention. For those who entertained the idea, the solar system itself became the test range, and the scientific community became the unwitting subject. At the same time, many researchers urged caution in attaching any narrative of design to ThreeI Atlast. They pointed out how easily human pattern recognition can overfit noise, especially when the story offers a sense of drama and meaning. Every comet that behaves oddly teaches astronomers something new about the flexibility of nature, and ThreeI Atlast might simply be the next lesson in that long series. Yet even the skeptics agreed on one point. The anomalies of ThreeI Atlast were strong enough and numerous enough that they forced open a door in the conversation. Behind that door sat the Bracewell idea, no longer a distant speculation, but a working hypothesis to compare against the data. Whether ThreeI Atlast ultimately proves to be an extreme comet, or something far more deliberate, the object has already served as a probe of a different kind, testing how far human curiosity is willing to stretch when the sky presents a puzzle that refuses to close. Long before most people had heard the name, ThreeI Atlast was already a quiet task on a mission schedule orbiting Mars. High above the red planet, the Chinese spacecraft Tianwen-1 followed its routine path, running through checklists, calibrations, and slow, careful slews across the sky. Somewhere in that sequence, a new target was added, a faint interstellar stranger, moving against the background stars. Engineers on the ground knew that Tianwen-1 had not been designed as a dedicated comet hunter. The spacecraft carried the TN-11 camera, a telescope with a mirror just under 40 centimeters, across small compared to the giants pointed from Earth, or the larger high-resolution imaging science experiment riding on NASA's Mars Reconnaissance Orbiter. On paper, the instrument was meant to watch Mars, not to interrogate visitors from beyond the solar system. Even so, the geometry was too good to ignore. From its orbital perch, Tianwen-1 would see ThreeI Atlast from a different angle than any observatory on Earth, looking sideways through the developing coma, instead of staring almost straight along the line to the sun. That vantage point turned a general-purpose camera into an unexpected window on Atlast. When the first exposure sequence was planned, expectations were modest. 3. Atlast was distant, faint and small, a difficult target for a mirror of that size. The team hoped only to pull a slightly sharper point of light out of the darkness, something that could confirm the preliminary orbit and hint at the beginning of a tail. The images that returned were not crisp portraits, but they were more than anyone had seen before. In the processed frames, ThreeI Atlast appeared as a compact bright core surrounded by a soft halo, a suggestion that gas had already begun to flow from the surface. The shape was smeared by motion and noise, yet the distinction between the central condensation and the surrounding glow was clear enough to make people lean closer to their screens. For the first time, humanity was not just tracking coordinates and brightness values for ThreeI Atlast. There was a picture, however rough, and that picture said that Atlast was active. The interstellar object was not a dead stone, but something capable of responding to sunlight in the familiar yet slightly skewed language of comets. Teams cross-checked the faint structures against stars and cosmic rays, making sure that the features really moved with ThreeI Atlast from frame to frame. Each pass through the data built a little more confidence that the blurred halo belonged to Atlast, and not to some artifact of the camera. Out of a handful of grey pixels, a new chapter in the story of this visitor began to form. The measurements still had wide error bars. Tianwen 1 could not reveal the fine internal pattern of jets, or the exact texture of the nucleus of ThreeI Atlast. Yet the combination of a condensed head and a modest asymmetric glow already hinted that Atlast did not behave exactly like the catalogue comets that had been imaged before. In the control rooms and offices where the pictures were passed around, a quiet excitement settled in. ThreeI Atlast was no longer just a track on a chart or a cluster of spectral lines. People could point to a frame and say there is at last a real object changing in real time under another star's light. Those early Tianwen 1 images did not answer any of the hardest questions. They did something gentler, and perhaps more important. They prepared the stage for higher resolution eyes and more ambitious expectations, and they whispered that ThreeI Atlast was worth watching for as long as it stayed within reach. While Tianwen 1 was quietly collecting its first pale frames, another spacecraft was gliding over Mars with a very different promise. NASA's Mars Reconnaissance Orbiter carried the high-resolution imaging science experiment HiRISE, a telescope whose mirror dwarfed the optics on Tianwen 1 and offered a far sharper eye for ThreeI Atlast. From that altitude, HiRISE could, in principle, do more than show a fuzzy glow around ThreeI Atlast. The camera was designed to pick out boulders and dunes on the Martian surface so the same resolving power turned outward might separate the core of Atlast from the surrounding haze. Engineers and scientists began to sketch what they hoped to see when HiRISE finally turned to ThreeI Atlast. In the best case, the camera would catch the narrow jets and the main tail from the side, revealing whether the apparent straightness around Atlast was a trick of perspective or a genuine disciplined structure. Modelers imagined a sequence of frames in which ThreeI Atlast would glide slowly across the field, its tail bending its anti-tail if present, drawing a fine counterline. If that pattern appeared, HiRISE could measure angles and widths, giving hard numbers to replace the guesswork that had surrounded Atlast so far. Orbit specialists were equally eager. With a sharper view of the central condensation, they could better estimate the size of the visible nucleus of ThreeI Atlast. Knowing how large the bright heart of Atlast really was would tighten the constraints on density and mass, and those values would feed directly back into the debate over the strange acceleration. In teleconferences, people spoke of ThreeI Atlast as if the visitor were a patient waiting for a decisive scan. HiRISE would not simply take pretty pictures of Atlast. The images would either strengthen the case that Atlast belonged to a family of extreme but natural comets, or they would pull the object deeper into the category of the unexplained. The geometry of the encounter added to the sense of anticipation. At key moments on its path, ThreeI Atlast would pass through an angle where Mars, the Sun and the Earth lined up in a way that let HiRISE see features invisible from the ground. From that vantage, Atlast might show subtle twists in the gas flows, or it might double down on the unsettling appearance of straight, unwavering beams. In articles and interviews, mission scientists spoke carefully about ThreeI Atlast, promising only that the data would be scientifically valuable. Behind the cautious language, there was a quieter layer of personal hope that Atlast would reveal enough detail to tip the balance between competing interpretations. For observers who had followed ThreeI Atlast from the beginning, the scheduled HiRISE window felt like a narrow door in time. Through that door for a handful of minutes, the solar system would offer its clearest look yet at this interstellar visitor before Atlast slipped farther away, taking its unanswered questions back toward the dark. As the orbit of ThreeI Atlast was refined with each new observation, the path on the charts grew sharper instead of softer. With ordinary comets, more data usually smooths out early oddities and drags the trajectory back toward the familiar. With Atlast, every new point nudged the solution further into uncomfortable territory. Computers traced the route of ThreeI Atlast backward and forward in time, plotting where the visitor had come from and where Atlast was going. The numbers agreed that Atlast moved on a retrograde track, slipping against the overall spin of the solar system. At the same time, the inclination of ThreeI Atlast to the ecliptic plane was surprisingly small, held within a handful of degrees, as if someone had carefully laid the path along the thin sheet where the planets circle the Sun. Most long-period comets cut steep angles through that plane, diving in and out like icy needles. 3. Atlast glided almost within it, crossing the orbits of the inner worlds in a way that made intersection points line up on diagrams like a string of quiet opportunities. Some dynamicists treated those alignments as coincidence, a natural outcome of drawing enough lines in a three-dimensional space. Others stared at the geometry of Atlast and felt a faint sense of deliberate placement. On top of this peculiar orbit, the behaviour of the jets around ThreeI Atlast layered another puzzle. Photometry and spectroscopy agreed that gas was leaving Atlast in organised beams rather than in a loose fog. Those beams appeared to hold a nearly fixed orientation in space, even as ThreeI Atlast rotated and curved along its retrograde path. In standard models, outgassing acts like a chaotic thruster, creating torques and random pushes that can twist a comet's spin axis and add jitter to the orbit. For ThreeI Atlast, the opposite seemed to be true. The non-gravitational acceleration of Atlast looked steady in both magnitude and direction, suggesting that whatever forces were acting on ThreeI Atlast were being applied in a remarkably consistent way. Attempts to reconcile this with a purely natural picture leaned heavily on geometry. Some teams imagined that the vents on ThreeI Atlast might be arranged so that, averaged over a rotation, the net push stayed almost constant. The idea was that Atlast could still be a natural body whose surface happened by chance to channel gas in a way that mimicked control. Even on paper, the range of vent positions and opening times that would produce the observed effect for Atlast felt narrow. When simulations tried to reproduce the straight sunward-oriented jets while spinning, ThreeI Atlast once every 16 hours, they often ended up with twisted ribbons instead of clean columns. To keep the jets of Atlast looking as they did in the images, modelers had to fine-tune parameters until the scenario sat on the edge of plausibility. Each small adjustment rescued one feature of ThreeI Atlast, while pushing another into conflict with the measurements. The combined picture was unsettling. ThreeI Atlast followed a retrograde orbit that hugged the planetary plane more closely than most distant visitors. At the same time, Atlast displayed thrust-like behaviour that seemed to push in a stable direction with jets that refused to twist and blur, the way textbook tales are supposed to. Taken separately, each oddity could be filed under the heading of rare but natural. Taken together, the orbit and the jets of ThreeI Atlast invited a different kind of question. If someone wanted to move quietly through a planetary system staying close to the main plane of traffic, while making slow controlled adjustments, the path might not look very different from the one Atlast was tracing now. That thought did not serve as proof, only as a bridge between unease and imagination. For many astronomers, the challenge was to explore every natural explanation to the limit before considering anything more exotic. For others, the consistent weirdness of ThreeI Atlast made it difficult to ignore the possibility that Atlast was behaving less like a passive rock and more like an object with a flight plan. As the discussions deepened, attention began to turn from the path of Atlast to the question of what kind of internal structure could support such disciplined behaviour. That quiet shift in focus set the stage for the next questions about the hidden heart of ThreeI Atlast. When the first rough images from Tianwen-1 and other telescopes were combined, a subtle pattern began to emerge around ThreeI Atlast. Beneath the soft coma, analysts could trace a compact central condensation, a bright knot that refused to spread out the way a loose powdery core usually does. ThreeI Atlast seemed to hide a small dense heart concentrating most of its activity into a surprisingly limited region. That impression grew stronger as models tried to match the observed brightness of ThreeI Atlast with plausible sizes and albedos. To shine as Atlast did at its distance, while still showing only a modest patchy active area, the nucleus had to be both dark and concentrated. 3. Atlast began to look less like a fragile porous snowball, and more like a shard of something that had already been cooked and compressed. Spectroscopic studies added another layer to that emerging picture. The gas and dust streaming away from ThreeI Atlast did not carry the exact chemical ratios catalogued in familiar comet families. Instead, several analyses pointed toward an unusually strong presence of heavier elements, especially nickel and iron compared to the amount of lighter ices that normally dominate such flows. ThreeI Atlast in chemical terms resembled the exposed core of an object that had once lived deep inside a different system's planetary architecture. If that interpretation is even partly correct, the story of ThreeI Atlast may have begun not in a cold distant cloud, but in the warmer, busier region near another star. In such a place, repeated cycles of heating, cooling and collision can strip away fragile layers and leave behind only the toughest materials. ThreeI Atlast would then be the survivor of that long process, a remnant core flung out into interstellar space after its home system rearranged or destroyed itself. This idea naturally leads to questions about what kind of star first warmed ThreeI Atlast. Isotopic hints suggest that the mix of elements in Atlas does not match the average recipe of bodies formed near our own Sun. ThreeI Atlast may carry the signature of a richer, older environment, perhaps from a stellar population that completed its main phases long before our system fully assembled. To many researchers, that possibility is quietly thrilling, even without any exotic engineering. A dense, metal-rich core like ThreeI Atlast would be a physical sample of a different planetary history, a fossil world compressed into a single wandering fragment. Atlast would then act as a small, silent envoy from a star that no longer has planets at all, or whose planets have evolved beyond recognition. At the same time, the structure implied by the data feeds back into the more speculative conversations. A nucleus as compact and durable as that of ThreeI Atlast is exactly the kind of chassis an engineer might choose for a device meant to survive eons between stars. The concentration of mass would help ThreeI Atlast resist spin-up tidal stress and micrometeoroid impacts, all while providing a stable platform for any internal channels or mechanisms. None of this proves that ThreeI Atlast is anything more than a remarkable natural relic. But each time the models are updated, the vision of Atlast as a dense, hardened core from an alien system grows a little clearer. ThreeI Atlast remains a point of light on the sky, yet in the numbers behind that light, astronomers can already feel the weight of a long and foreign past pressed into its hidden heart. The schedule for the high-rise observations of ThreeI Atlast was set months in advance, marked on internal calendars like a quiet promise. Teams knew the windows when Mars, the Sun and Atlas would line up just right, and they cleared time in the planning tools to point the camera away from the planet and into the dark. When the crucial days passed, people waited for the usual signs that data from ThreeI Atlast had arrived. Under normal circumstances, raw frames move quickly through the pipeline, picked up by automated systems, tagged, stored and passed on to teams for cleaning and analysis. This time, the expected images of ThreeI Atlast did not appear on the usual dashboards. The first explanations were practical and dull. Operations teams mentioned scheduling conflicts, a backlog of higher priority tasks, and the simple pressure of running a complex mission with limited staff. Government disruptions had also slowed some review processes, and that delay spilled into the schedule that controlled when ThreeI Atlast would be processed. Weeks went by, and in that slow gap, attention sharpened. Astronomers outside the core teams began to ask whether the high-rise data on ThreeI Atlast had actually been taken. Public logs suggested that observations had been made, but the absence of even preliminary thumbnails fueled a sense that something was out of step. When the first images of ThreeI Atlast finally surfaced, they were not the clean, expansive scenes many had imagined. The frames were tightly cropped around the core, compressed more than usual, and stripped of much of the context that helps interpret a difficult target. Researchers searching for the full raw set of views of ThreeI Atlast ran into missing links and short explanations about storage limits and calibration requirements. Officials stated that the treatment of the ThreeI Atlast data followed standard procedures adapted as necessary for bandwidth and processing priorities. From a technical standpoint, those reasons were plausible. Yet for scientists who had invested so much expectation in a decisive look at ThreeI Atlast, the gaps in the record felt louder than the explanations. Requests for more complete access to the ThreeI Atlast images were submitted through formal channels. Letters and emails pointed out that the unusual behaviour of ThreeI Atlast made the data of broad scientific interest, and that transparency would help settle growing speculation. Responses arrived slowly, often restating policies, without directly addressing why certain frames of ThreeI Atlast seemed harder to obtain than others. In the absence of a simple, satisfying narrative, people began to write their own. Some remained convinced that the handling of ThreeI Atlast was no more than bureaucracy and strain on an overworked system. Others wondered whether the most striking views of ThreeI Atlast had revealed structures awkward enough to trigger extra caution before release. None of those stories could be confirmed. ThreeI Atlast continued along the plotted orbit, indifferent to the timing of human paperwork and public image archives. What settled in the community was not a clear accusation, but a lingering sense that the sharpest glimpse of ThreeI Atlast had passed through a narrow bottleneck of decisions that no one fully understood. That feeling quiet and unresolved followed the object into the next phase of its journey, where attention would shift from delayed images to the deeper history written inside the material of ThreeI Atlast itself. The days around perihelion were supposed to be the most dangerous in the life of ThreeI Atlast. Astronomers watched as Atlas plunged deeper into the sun's glare, expecting the usual story of stress cracking and slow unravelling. Reports instead began to describe a different script. 3. Atlast flared in brightness through a series of violent interactions with the solar wind, each spike suggesting shock and turbulence in the gas around the nucleus. Telescopes registered sudden changes in the coma and tail, as if Atlast were shaking off layers under a storm of radiation and charged particles. Yet when the glare eased, and images could be processed more carefully, ThreeI Atlast was still there. The core of Atlast had not broken into a spray of fragments, and no obvious debris field marked a terminal event. Instead, new structures, sharper jets and altered brightness patterns suggested that ThreeI Atlast had passed through the encounter changed but intact. For some observers, this resilience made Atlast look like a natural experiment in extreme heating and cooling. For others, the survival of ThreeI Atlast under those conditions felt more like a stress test passed by design. Either way, the stage was set for the next question. After such a trial, what new signals would Atlast send back into the waiting dark? After the storm of perihelion, a strange quiet settled around ThreeI Atlast. For days and then weeks, telescopes reported only steady dimming, as if Atlast were withdrawing into the cold again. Then, almost without fanfare, a radio array listening near the right frequencies caught a whisper. The signal was not a burst or a beacon, but two thin absorption lines, the spectral fingerprint of hydroxyl gently etched into the noise. ThreeI Atlast, which should have been cooling and calming, suddenly showed the telltale sign of fresh water vapour breaking apart in space. Under ordinary comet physics, the timing felt wrong. Heating peaks near closest approach and gas release usually fades as the nucleus turns away from the sun. Here, ThreeI Atlast seemed to wait through the brightest phase, then exhale once the glare had begun to ease. Modelers tried to picture hidden reservoirs, deep pockets of ice, that might only vent once certain angles or cracks aligned. In those scenarios, ThreeI Atlast became a kind of mechanical lung, taking its time to open a valve after the worst of the heat had passed. For observers, the hydroxyl lines felt less like a shout, and more like a deliberate murmur. ThreeI Atlast had gone silent, then chosen a quiet, narrow moment to speak again. That small, disciplined rise in a familiar chemical signature became a bridge between simple melting and the unnerving idea of a controlled, almost conversational release. Long after the glare of perihelion faded, the orbit calculators noticed something that did not belong to the calm tale of the story. ThreeI Atlast was no longer following the curve dictated by gravity alone. Predicted positions and measured positions began to drift apart in a smooth, stubborn way. Night after night, Atlast arrived slightly ahead of schedule, as if a gentle, invisible hand were helping ThreeI Atlast along its path. The extra push did not surge or flicker. The magnitude and direction of the non-gravitational acceleration stayed remarkably steady, like a soft engine holding one quiet setting. Under standard models, such behaviour would require a particular pattern of outgassing. ThreeI Atlast would need to vent mass in a stable asymmetric way, losing material at just the right rate and from just the right regions to keep the push aligned. For a while, some teams treated Atlast like an extreme example of that delicate balance. Then the acceleration eased. The steady drift of ThreeI Atlast fell back toward the tidy line of a purely gravitational orbit. Around the same time, new images showed 5 persistent plumes, one aimed nearly toward the sun, and the colour of Atlast shifting from a warm dusty red to a cooler metallic blue. That change in hue suggested different materials on the surface, richer in nickel and iron, had taken over the visible show. ThreeI Atlast looked less like a fluffy wanderer and more like bare alloy exposed to the light. For some, the sequence felt like a natural crust burning away to reveal a tougher core. For others, the calm acceleration, the sudden return to gravitational obedience, and the metallic glow of Atlast all whispered of a system that had adjusted itself and then settled back into silence. When isotope specialists finally turned their attention to ThreeI Atlast, the age estimate felt like a shock. Ratios of oxygen and carbon in the material around Atlast pointed not to a young system, but to a stellar nursery that had burned bright billions of years before our sun fully formed. On their screens, ThreeI Atlast became a time capsule from roughly 7 billion years in the past. The chemistry of Atlast suggested an origin in an older, richer stellar population, where generations of stars had already lived and died. Backtracking the orbit added another stranger thread. When analysts extended the path of ThreeI Atlast backward through the galaxy, the line swept past the sky region, where in 1977 a narrow, unexplained radio burst had been recorded, and later nicknamed the WOW signal. The match was not perfect. The angular separation between the reconstructed approach of ThreeI Atlast and the original WOW direction sat around several degrees close enough to stir interest, but too wide for easy conclusions. Statisticians tried to weigh the odds that an ancient metal-rich visitor like Atlast would wander near the same patch of sky that once hosted a famous one-time radio anomaly. Rough estimates suggested that such a double coincidence in both chemistry and direction was not impossible but far from comfortable. For cautious minds, ThreeI Atlast remained an unusually old fragment, whose path merely grazed a storied coordinate. For others, Atlas began to look like the fossil of an interstellar effort that had outlived its makers drifting past our system, just close enough to remind us that somewhere in the deep past, someone else might once have tried to speak.